The first topic is integer programming. An integer programming model is a model that has constraints and an objective function identical to that formulated by linear programming. The only difference is that one or more of the decision variables has to take on an integer value in the final solution. There are three types of integer programming problems. Solution values must be whole numbers in integer programming. Those three types are pure integer programming and mixed integer programming and 0, 1 integer programming. Pure integer programming problems are cases in which all variables are required to have integer values. Solving an integer programming problem is much more difficult than solving an LP problem. The solution time required to solve some of these may be excessively longer than the normal linear programming. Mixed integer programming is cases in which some but not all of the decision variables are required to have integer values. So some of them are continuous variables, some of them are integers. And in that case, we also will learn how to run integer programming there. 0, 1 integer programming is binary programming, are special cases in which all the decision variables must have integer solution values of 0 or 1. And we will look into these topics one by one. A. Pure integer programming. Harrison Electric Company. Harrison Electric Company is located in Chicago's Old Town area, and it produces two products popular with home renovators: old-fashioned chandeliers and ceiling fans. Both the chandeliers and the fans require a two-step production process involving wiring and assembly. It takes about 2 hours to wire each chandelier and 3 hours to wire each ceiling fan. Final assembly of the chandeliers and fans requires 6 and 5 hours, respectively. The production capability is such that only 12 hours of wiring time and 30 hours of assembly time are available. If each chandelier produced nets the firm $7 and each fan nets $6, Harrison's production mix decision can be formulated using LP as follows. Maximize profit equals $7 times the number of chandeliers and $6 times number of fans. And the constraints are first wiring hours. It takes 2 hours to produce chandeliers, so 2 times x1 plus 3x2. It takes 3 times to produce fans. And the total wiring hours that this company has at this moment is 12 hours. And similarly, assembly hours, it takes 6 hours for chandeliers and 5 hours for fans. So we have 6x1 plus 5x2, which is less than equal to 30. And x1, x2 are assuming non-linearity and non-negativity. Now this is a graphical solution of this Harrison Electric Company. With only two variables and two constraints, Harrison's production planner employed a graphical LP approach that we have learned a lot, in the first chapter, and generated an optimal solution for X1, and it turns out to be 3.75 for X1 here, and for X2, the fan, it's 1.5, so 3.75 and 1.5. Recognizing that the company could not produce and sell a fraction of a product, the manager decided that he was dealing with an integer programming problem. Listing all feasible solutions and selecting the one with the best objective function value is called an enumeration method. Obviously, this can be quite tedious for even small problems, and it is virtually impossible for large problems, as the number of feasible integer solutions is extremely large. But look at this table. We enumerated all the solution for integer program. For example, 0 to 0, and the profit is 0, and use produce only one x1, and then 0 fans, then right here, and at that time you're going to produce about $7. So it produces all the combinations there, and then corresponding profit there. And we find that if you just round up 3.75 and 1.5, then you might have 4.2, which is just outside of the feasible area. So you may not be able to produce this point at all, and it is not possible. In that case, you can say round up for x1 and round down for x2, then you get, say, 4.1, and that's certainly feasible, and it will give you a good profit, and you can take a look at that too. Or you can round down for x1 and round up for x2, then you have 3.2, right? 3 and 2 as your coordinate, and then this might be your uh, point that gives you a good profit. So if you look at that, for example, 4.1, that's $34 of profit it gives, or 3.2, if you can see 3 and 2, it gives even lower profit, which is $33. And it happens that the highest profit takes place when chandeliers are produced. Five of them are produced, and the 0 fans are produced. At that time, you're going to make the best profit, which is $35. So this case demonstrates to us that rounding up and rounding down, finding the nearest solution may not necessarily be the best solution for your case. So therefore, we need to really find a way to do this integer programming so that this integer program might be able to find the best point for your case or problem. So here is a Excel solver solution that I did for you. So I put variables first, x1 and x2, and then variables are started from 0 or nothing, and I put the coefficient 7 and 6, and maximum profit was calculated here using some product function, and then I also put the constraints x1 and x2 and wiring hours and assembly hours there, and left-hand side and sine and right-hand side, and ran Excel solver as I specified here, and then found that when I use the integer, look at here. So L4 and M4, which is L4, so L4 and then M4, these are actually integers that I specified as a uh, um, constraint, and then added these two constraints there and ran it, and then I found that 0, 6, right? That was the best solution in this case.